Okay, so good afternoon, everyone, whether online or in person. I would like to welcome you to the second part of the series of Nirenberg Lectures in Geometric Analysis. The two last talks will be given by Wang, who is a professor at Courant Institute of Mathematical Sciences and equally at IHES in France. Professor Wang has received her PhD in 2019 from MIT and following a postdoctoral position in the Institute of Advanced Studies, she went and joined the faculty of UCLA. In 2023, she moved to Courant Institute, where she is currently still a professor. And she is an expert in Fourier analysis and geometric measure theory. She's well recognized by prizes such as the Mariam Mizrakani New Frontiers Prize in 2022 and an invitation to speak at the ICM in 2026 next year in Philadelphia. And today's lecture will be a continuation on the Kakeya conjecture, will be on the Kakeya sets in R3. And tomorrow talk will be a general talk. Probably we'll hear about the restriction conjecture, where Professor Wang is, on which Professor Wang is an expert of. In any case, it's a general talk, so I encourage you to attend also tomorrow's lecture at 3:30. So now I'll give the floor to Hong Wang.
Thank you very much for the very nice introduction and also the invitation. It's a great honor to deliver the second part of the Nirenberg Lectures. I'm sorry I cannot be there in person. I always wanted to visit Montreal, maybe next time. So I will be talking about union of tubes in R3. This is joint work with Josh Zahl, and also I hope this talk is accessible to everyone, so please feel free to stop and ask questions. For those who are online, feel free to unmute yourself and interrupt at any time. So let's look at the setup. So we have delta that's a small scale, and we consider a set of delta tubes that has radius delta and length 1. And we say that two delta tubes, T1 and T2, are distinct if their intersection is small. So for example, this tube, the blue tube, is distinct to the white one. But if I draw the blue tube this way, then it's not distinct. And the object that we want to study is a set of distinct delta tubes, let's say, contained in a unit ball in Rn. This unit ball is not that important. One can think of any ball of, say, constant radius. And the question we care about is how large is the volume of union of tubes in T? That is, if we take the union of all delta tubes in T and we want to have a lower bound on its volume. Why do we care about this problem? As we will soon see later, the Kakeya problem can be rephrased as a problem of union of tubes. And also those long skinny tube can represent the geometry of waves, of, for example, the Schrodinger waves. And if we combine such estimate with some recent tools in harmonic analysis, usually this gives rather strong bounds on oscillator integrals. So now let's start with, I know Josh has already talked about Kakeya conjecture for 2 talks. So let me remind you that the Kakeya conjecture can be rephrased as follows. Or some equivalent version. So if a set of tubes, so T, contains a delta tube in each delta separated direction, this means that we take from the unit sphere, we take a delta net, and then in each of this direction, we have a delta tube. Then the union of those tubes in T has volume approximately 1. And also, one should consider those delta tubes as contained in a ball of radius 1, for example. And this approximate means the following. it is up to a factor of delta to the epsilon, and epsilon goes to 0 as delta goes to 0. Because as Josh talked about, there's a coverage construct an example saying that this cannot be constant. It has to go to 0 as delta goes to 0. So this approximately equal to 1 just means like subpolynomials of delta. So we call this T contains a delta tube in each delta separated direction as the Kakeya assumption. We use this K to denote the Kakeya assumption. Why? Because the original definition of Kakeya set is a compact subset of Rn that contains a unique line segment in every direction. So this is, we look at things at resolution delta, and this is a delta discretized version of the Kakeya assumption. And this assumption in particular implies that the number of delta tubes is approximating or greater or equal than delta to the minus n minus 1, because if the number of delta separated direction on the unit sphere in Rn is delta to the n minus 1 up to a constant multiple. If one can answer this question, if one can solve this conjecture in all dimensions, then one can prove the Kakeya, the original continual version of the Kakeya conjecture in all dimensions. And today we are going to focus on dimension 3. One can also ask a more general question about union of tubes, and later we will see why we need to study this more general question, even if we just wanted to understand. We just want to understand the Kakeya problem, which is some more specific question. So the more general question is, for what collection of delta tubes, the union of tubes has volume approximating, again, this approximating means subpolynomial delta, the minimum of the number of tubes times the volume of a single tube, which is delta to the n minus 1, and 1. 1 is the approximately the volume of a unit ball. So here I should add the assumption that for what set of delta tubes contained in the, let's say, contained in the unit ball. Because everything here we are considering is compact. This general question, if we rephrase it in a different way, the first term means that if the union of those tubes has volume approximating the number of tubes times the volume of a single tube, this means that, roughly speaking, the delta tubes in this collection are essentially disjoint. So that's what the first term means. And the second term means that since all the tubes are contained in the unit ball, the second term means that they have to essentially fill out the unit ball. This volume bound is the optimal, is the largest we can get, because the union of tubes cannot be more than this, and also not more than the volume of a unit ball. So proving the Kakeya conjecture reduced to, let's say, not really reduced to, but is like saying, is the set of tubes satisfying the Kakeya assumption lies in this class of the set of tubes that solves the question star. If we want to study this general question, immediately we find some enemy example that we need to be careful. So one enemy example is the following. Let U be a rectangular box. Let's say it has length 1 and the smallest side length is greater or equal than delta. That means it contains more than one delta tube, so that the problem is non-trivial. And we can take T to be all distinct delta tubes in U. So remember that distinct means that the tubes are not like overlapping a lot and they don't look like it's the same tube. So this is distinct. So how many tubes, delta tubes, are there in U? All distinct. They can overlap, like they can overlap a lot, but they cannot be essentially the same one. So this picture is not distinct. The first picture is distinct. So if you do some calculation, think about it carefully, then the number of such tubes is the volume of U divided by the volume of T squared. So this could be a fun exercise to do. I also included some explanation here that I put it in small, but if one would like to know how it works, I'm happy to answer in the end of the talk. But I think it's a fun exercise. But then the union of those tubes has volume at most the volume of U because they are all contained in U. So if we look at this example, then for sure it does not satisfy the question star because the union of tubes has volume U. This is U. But then this term, the number of tubes times T this is the number of tubes, is much larger than the volume of U because if U is a rectangular box that's much larger than a delta tube and much smaller than a unit ball, then this term is much larger than, so in this example, this term is much larger than the volume of U. So that's why it's an enemy example. It turns out that in R3, this is the only enemy example. And that's what we proved. That I think that summarized what we proved in our last paper. But before that, let's say if we know such an enemy example exists, and we still want to answer this question, how shall we do? First, we need to say that our set of delta tubes should avoid this example. And this means that if we let TU be the set of tubes containing U, then we want to say that the number of tubes in U is less than the volume of U divided by the volume of T, because this is what's needed such that when it's U and then this term matches the volume of U. Maybe it's a good time to pause and see if there are any questions.
No?
Okay. Yeah, it's a little hard to give an online talk because I cannot see the audience. Okay. So inspired by this enemy example and also our observation that in order to rule out this enemy example, this is one assumption that we should consider. So as we mentioned, like it turns out that this is the only enemy example in dimension 3 and also dimension 2. In high dimensions, there will be new enemy examples that appear. So for the rest of the talk, let's focus on n equals to 2 and 3. So let's give this criteria a name. That is what we call the Kastel-Wolff axiom. So if T is a set of delta tubes containing a unit ball, we say that T satisfies the Kastel-Wolff axiom. We write it KT for short. If for any rectangular box U contained in the unit ball, the number of tubes contained in U is less than the volume of U times divided by the volume of T. So as we pointed out in our calculation, this is a necessary condition for the question to for T to satisfy this bound, the optimal bound. And since U is contained in the unit ball, if we just take the U to be the unit ball, then this means that the number of tubes is less than 1 over the volume of T. So this gives them an upper bound on the cardinality of tubes. The reason why we call it Kastel-Wolff axiom is the following. So first of all, the Wolff axiom is because originally this is Wolff. He formulated this Wolff axiom in his inferential paper on the hairbrush estimate bound on the Kakeya set. And he says he made the key observation that in order for his estimate to hold, then there shouldn't be too many tubes contained in plane slab. And this is a mild generalization of that. And this Kastel is related to some notion of Kastel delta S set in geometric measure theory. Then we also need to, so we would guess naturally that a set of tubes satisfying the Kastel-Wolff axiom, that it will saturate this bound, means that we would guess that any set of tubes satisfying the Kastel-Wolff axiom, so this enemy is ruled out, and so we hope that the union of tubes has volume approximately the number of tubes times the volume of single tube. Then what about this term? There is another scenario that's sort of dual to the Kastel-Wolff axiom, that is the Frossman-Wolff axiom, which is in geometric measure theory, the name Frossman comes from Frossman lemma for Hausdorff dimension. So we say that the set of tubes satisfies the Frossman-Wolff axiom if for any rectangular box U, the number of tubes contained in U is less than the volume of U times the total number of tubes. This means that there cannot be too many tubes containing any rectangular box with respect to the total number of tubes. So in particular, if we take U to be one single tube, then this number is at least 1. And this shows that the number of tubes is at least 1 over the volume of a single tube. So this gives us a lower bound on the number of tubes. That's why these two conditions are sort of dual. This is the key condition that allows us, the key definitions that allows us to study this general question of union of tubes in R3. Here are some remarks that help us to digest this notion. So first of all, this definition allows parallel delta tubes. So this is very different than how we thought about the Kakeya set in many years ago. The reason is that the definition of a Kakeya set, or the Kakeya assumption, says that the set of tubes has one delta tube in each delta separated direction. It seems that this direction separation, or like one tube in every direction, is the key feature of the Kakeya set. But it sounds, but in reality, to solve the problem using our approach, it doesn't really matter whether the set of tubes has distinct directions, or each direction there is one delta tube. So for example, this T, there is an simple example saying that if we just choose one direction theta, a fixed direction theta, then we take T to be all distinct delta tubes in direction theta, means that we take many parallel tubes in the same direction. And then such T is both Kac-Tal and Frostman, because we take all the distinct delta tubes that's contained in uniball in the same direction. And in particular, it satisfies this assumption, like it is one set of tubes that has this property, that the union of tubes has volume equals the minimum of the number of tubes times the volume of a single tube and 1, and in which case both of terms equals to 1. Well, another example is the Kakeya assumption. That's a set of tubes contains one tube in every delta separated direction. It is also both Kac-Tal and Frostman. So these two sets of tubes seems to have sort of the opposite, properties. One is only one direction and many parallel tubes, and the other one says, well, at each direction only one tube. And this seems like the opposite properties, but they share the same consequence for when we study the union of tubes. Similarly, we can sort of interpolate these two extreme examples and get a sequence of a family of examples that satisfies the optimal bound for the union of tubes. And those class of examples are the sets that satisfies the Kac-Tal-Wolff axiom and the Frostman-Wolff axiom. So in dimension 2 and 3, I think the key starting point is that we figure out this right definition, inspired by previous work of Tom Wolff and Katz and Tao. So here is our main theorem. I included the dimension 2 case, which is proved by Cordoba in the 1970s, and also the dimension 3 case by Josh and I earlier this year. If a set of tubes satisfies the Kac-Tal-Wolff axiom, then the union of tubes has volume approximately the number of tubes times the volume of a single tube. In other words, if a set of tubes satisfies the Kac-Tal-Wolff axiom, then they are essentially disjoint. And there is this dual part. If a set of tubes satisfies the Frostman-Wolff axiom, means not too many tubes contained in any rectangular box with respect to the total number of tubes, then the union of them should have volume approximating 1, means that they should essentially fill out the unit ball where they lie in. So that's our theorem. And since the Kakeya assumption satisfies both Kac-Tal and Frostman, and this implies that our previous conjecture about the Kakeya delta discretized Kakeya conjecture in dimension 2 and 3 is true. Well, dimension 2 was proved by Cordoba, but our new theorem is in dimension 3. Yeah. So let me pause and see if there are any questions. Okay.
You mentioned the
yeah.
the Frostman-Wolff axiom.
Yeah.
I'm just wondering how this subject is related to the work of Frostman.
Yeah. So that's so the Frostman, the name Frostman comes from Frostman lemma, saying that any set of Hausdorff dimension S, there exists a measure on this set such that the measure mu on any ball of radius rho is less than, say, rho to the s, right? So this rho to the s plays the role of u. So it's inspired by this Frostman lemma. The name comes from Frostman lemma. In fact, if we look at dimension n equals to 2, and we pass to the dual space, sorry, not the dual space, the parameter space for the set of tubes, each tube corresponds to one parameter, then this recovers the Frostman lemma, or the Frostman delta S set. I hope
Thank
this
you.
Yeah, thank you. Okay. So another just one remark is that one should think this as some sort of a symmetric version of the more classical Frostman condition, because the rectangular box can have different side length. And I think that's a very important feature for when we study union of tubes in R3, is that we should take into account rectangular box of different shapes rather than just a thicker tube. So this is I think it's a very important part. So now let's go back to the proof. I know Josh talked about sticky Kakeya in his last talk. I just want to show you some pictures. So here, the right notion of stickiness. For the union of tubes in R3 is should be the follows. One right notion. The set of tubes T satisfies the Kastner-Wolff axiom at all scales. So what does it mean? I will remind you the definition in the next slides, but let me show you this picture. So the left-hand side and the right-hand side, they both satisfy Kastner-Wolff axiom. But they are different. So what does it mean to satisfy the Kastner-Wolff axiom? It means, okay, let me just remind you here. It means that for any U, the number of tubes containing U is less than the volume of U divided by the volume of T. So this is, what does it mean T satisfies Kastner-Wolff axiom? And both examples satisfies because both example does not have too many tubes containing any rectangular boxes, if you look at it carefully. However, the left-hand side does not satisfy Kastner-Wolff axiom at all scales, because if let's take those row balls, if we take the row neighborhood of those tubes, we get a set of, and we take a set of distinct row tubes that covers the original delta tube. So that's those purple tubes. Then we see that there are a lot of those purple tubes, and it's too many, so that the purple tubes are not Kastner. This means, later we'll see the definition, this means that the left-hand side does not satisfy Kastner-Wolff axiom at all scales. However, the right-hand side, as we can see, if we thicken it to a row tube, those green tube, they are still somewhat sparse, and it still satisfies the Kastner-Wolff axiom. And so this means all scales, and this means not Kastner all scales, but both of them are Kastner. So here is the definition. A set of tubes T satisfy Kastner-Wolff axiom at all scales if for any row, if we thicken them, then the thickened tubes is still Kastner. So that's what this picture says. And this definition is great because we could do induction on scales. So because both thickening and restricting satisfies Kastner-Wolff axiom at all scales. So this takes some time to digest, but using this definition, it's not hard to show that both thickening and restricting and rescaling satisfies Kastner at all scales. And this means that Kastner at all scales is a good class of tubes to do induction. In the study of problems in geometric measure theory, especially in recent developments, it's really important to find the right class of sets to induct. You don't want your class to be too big, because then you need, in order to deal with all cases, you need to be more involved. You also don't want your class to be too small, in the sense that, okay, but if it's too small, then your induction assumption might not be strong enough to close it. So one of the main difficulty is to find the right class of sets to induct. So it turns out that stickiness, in our version of stickiness, it means that the set of tubes satisfies Katz-Tau-Wolff axiom at all scales is the right class of sets to induct. And this is indeed what we proved. So I think this statement is proved in our second paper, but the method is essentially the same as in the first paper. But I think it's a crucial, it's like psychologically a crucial step. That's once we figure out the set of tubes is Katz-Tau at all scales, and then we have the theorem. We have the desired inequality, that is the union of tubes has volume approximately the number of tubes times the volume of a single tube. Or in other words, if the set of tubes is Katz-Tau at all scales, then they are essentially disjoint. So our final theorem removes this at all scales. So this is sticky and this is general. It seems like we just removed 3 words, but it takes a lot of effort. So the goal for today is use this theorem, the sticky Kakeya theorem, as a black box, and then to prove a general theorem. In other words, the goal is to remove these 3 words. The tool is to use induction. How do we do that? So the goal is to show that if a set of tubes is Katz-Tau, then the union of tubes has volume approximating number of tubes times t. And we said that it means that the tubes are essentially disjoint. In other words, the multiplicity, mu t, multiplicity means the number of tubes through a typical point, is less than 1, bounded less than, approximately less than 1, up to subpolynomials of delta. So these 2 statements are equivalent. And the way we are going to use induction is we are going to use a self-improving argument. So suppose we know the following statement. If the set of tubes is Katz-Tau, then the multiplicity is bounded by the number of tubes to some beta. So beta equals to 1 is trivial because the number of tubes passing through a single point is at most the total number of tubes. So beta equals to 1 is trivial, and the goal is to show that beta equals to 0. So suppose we know this statement for some positive beta, and we want to show that, in fact, this should hold for some smaller beta. Since we know how to prove the sticky case, that's our theorem 1, we can assume that the set of tubes is not sticky. So what does it mean when the set of tubes is not sticky? So not sticky means that in this picture, it means it satisfies Katz-Tau, but not at all scales. So what is a good candidate? That's the picture on the left-hand side, which means in this picture, we see a lot of row tubes. So that is our intuition. We start with a set of tubes that's not sticky, and there exists some row that we see a lot of row tubes, means the number of row tubes is much greater than rho to the -2. That's the purple tubes. yeah, I should have drawn this purple. So what are we going to do induction on? So we are going to analyze multiplicity because our induction hypothesis is set up using multiplicity bound. So let's say this yellow point is a typical point, and then those yellow tubes are delta tubes. And what is the multiplicity here? The number of delta tubes through one point, as we can see, is 1, 2, 3, 4, 5, 6. We have 6 delta tubes through one point. And we can regroup those delta tubes inside a row tube together. And since the delta tubes in row tubes, when they intersect, since they have small angle, they intersect into some tube segments rather than a single point. So this is the tube segments. If we calculate, then the tube segments has length delta over rho, because this angle separator is rho, and then this is delta. The width is delta, or the radius is delta, and the length is delta over rho. After some pigeonholing, we can decompose the multiplicity as follows. The multiplicity, the number of tubes through a point, is approximately equal to the number of tubes inside a typical row tube through each point. In this case, is 2 times the number of those segments through each point. And the segments, we are going to call them grains. So here, like, as we can see, 6 equals to 2 times 3. And the first picture holds in general. And the second picture is what in the past people usually use, is the number of thin tubes through each point is bounded by the number of thin tubes inside a thick tube times the number of thick tubes passing through each point. And as we can see that here, there might be some other thick tube that passes through this point, but there are no thin tubes containing the point. So in the past, this is how I would think about the problem in grad school. And this is wasteful because when we are at a very non-sticky case, the number of row tubes, those green tube, can be much greater than rho to the -2. So even on average, we expect a lot of row tubes passing through any point. So one key starting point is that we use the first lossless decomposition instead of the second one, where people tend to think about. And there is a reason why we tend to use the second bound, because those row tubes are just thickening of the previous tubes. So we still have some sort of information about those row tubes. We know that at any row separator direction, there should be a row tube, except that there might be many row tubes in each direction. So the objects involved in the second decomposition are more familiar, even though they are harder to deal with. However, in the first lossless decomposition, the key difficulty is that those grains, those tube segments, we do not have any control of. It comes from the tube intersection, and a priori we don't have any information about it. And here is, I would say the reason. So we use the first decomposition, and we study those grains intersection carefully. And the reason why we can do it is also based on some recent developments in projection theory, saying that for any some of the key idea is that for any set of tubes, we could find some structure. And this fits our problem because if we want to use this lossless decomposition, we are facing a set of grains that we don't have any information. And that is why we need some idea how to study a collection of those tube segments with no a priori information. So, but there is still something we can do. So first of all, the grains has side length delta over rho and radius delta. If we rescale it to become this, radius becomes, the side length becomes 1, and then the radius will become rho tube. So there is a reason that these two things has the same dimensions. This means they are meant to be compared. So this is what people used to use, and it's wasteful, but we have information. And this is not, this is sharp, but we don't have any information. It's probably hard to deal with. And they have the same dimensions, means that those objects are the real objects that we need to study in place of these ones. And how do we study it? So this is, I think, one of the main ideas underlying lots of developments in projection theory. I mean, this it's not our factoring proposition, but the idea that lies behind those finding structure from no structure was inspired by Schmerkin's multi-scale decomposition. So what Schmerkin says that truth is, if we have a set of delta balls, and then using after some pigeonholing idea for again, we can find those uniform subset. And then Schmerkin observed that this uniform subset, we can find not too many scales such that between scales, we have genuine, some like as some fractal set. And this is the factoring proposition that we're going to discuss next is like a two-scale decomposition. But Schmerkin has multi-scale decomposition, but this is a two-scale but asymmetric decomposition. So what does it say? Is I found this picture of spaghettis online. I think this fits the description of factoring proposition a lot. So suppose we have a random set of spaghetti, which is thin, skinny tubes. Then we sort of want to find some boxes to contain them. So here a natural box is this one and this one. And how does it have anything to do with factoring proposition? It says that let T be a set of rho tubes contained in a unit ball. Then, so an arbitrary set of rho tubes. Then we can find two numbers, A and B. Those A and B, and so we are not given a priori. It's determined by the set of tubes. And a set of A times B times 1 boxes. So those are the envelopes and the refinement of T. Sometimes we need to throw out some small fraction of tubes, such that the boxes themselves as a collection is Kastel. So even though I didn't discuss what Kastel-Wolff axiom for a collection of boxes mean, but this just means that it's not too hard to generalize. This means that for any rectangular box U, the number of A times B times 1 boxes contained in U is less than U divided by the volume of a single box. And that is the Kastel mean. And so following our previous intuition, what we aim to prove, W is Kastel means that the set of W's are essentially disjoint. And then the second part is for any box, the tubes contained in this box is Frostman within W. What does this mean? It means the following. For any V contained in W is less than V, we need to renormalize with respect to W. And this is 1, and this is 2. And also each tube is contained in approximately 1 box. So let's stare at this proposition and then try to combine with what we aim to prove and digest. So this proposition combined with what we want to prove says the following. For any set of tubes, we can find a collection of boxes such that the tubes will essentially fill out the boxes. So we should think the boxes are full of tubes. And then the boxes themselves are essentially disjoint. And so for now, that's just an intuition. We haven't proved that the boxes are essentially disjoint. We also haven't proved that they essentially fill out this box, but this serves as good intuition. And now let's recall that why do we need the factoring proposition is because
Oh no.
I think my video was off, but
Yeah.
can you still look at this and see the screen?
No, can you share again?
Yeah, I think I'm sharing now.
Okay, now it's fine.
Yeah, can you remind me when I was offline?
Or you only went for a few seconds, so you were still with the boxes,
Okay,
satisfying
thank
the
you.
conditions, and
Okay, thank you.
back.
Thank you so much. So the reason why we want to use this factoring proposition is that let's go back. Like this is the lossless decomposition, and then we need to study the grains, and then, but we have no a priori information about the grains. So this could be an arbitrary set of tubes. And then the factoring proposition tells us that we can find some boxes to sort of classify them. And now we have to study case by case. So those, as we said, that the boxes are not given, not determined by us, is given by the set of tubes. So in one extreme case is that the set of those boxes has the same dimension of those tubes. So in other words, each box is just one tube. Then what do we know is that the boxes are cast-out. This means that the set of grains is cast-out because we apply this proposition with the set of grains in place of T. So when the set of grains is cast-out, then recall that by induction, we know that with our induction hypothesis is if any set of tubes is cast-out, then the multiplicity is bounded by the number of tubes to some beta, and we want to make our beta smaller. And this multiplicity bound, the number of tubes through a point is bounded by the number of tubes inside a row tube through each point times the number of number of grains through each point. So this bound is the lossless decomposition here. Is this decomposition? This is mu t, and this is mu t inside row, and this is mu grain. So we have this decomposition, and by induction, the first term is bounded by number of tubes in T row to the beta. And by induction, we also know that this is bounded by number of grains to beta. But since here comes the key improvement from T being non-sticky. If the set of tubes is not sticky, then the number of row tubes is much greater than rho to the -2. However, since G is Kastel, the grains is Kastel means that the number of grains is less than rho to the -2. So these two information altogether says that this mu grain is much smaller than number of row tubes to beta. So this is beta. And adding together, this means that the actual multiplicity is much smaller than what the induction hypothesis says, which means that we have an improvement. So we get a first improvement if the set of grains is Kastel. And there are, of course, other cases. If the boxes are much thicker than a row tube, so using our intuition, we know that those tube segments should essentially fill out this box. And if the box is thick, this means that we can thicken everything to a larger scale and apply induction. And since we know it's essentially fill out the box, it means that we have a large density here. So overall, we have a density improvement. So I didn't state any formulas. I would just say proof by picture. And then the third case is most interesting case. It's tricky because if the boxes are thin, has the same thickness as row, but it is wide, because if it's not wide, then we are back to the first scenario. Then we know that the union of tubes is approximately the union of those boxes, the grains, and the grains now fill out those thin boxes. And we need to study those the intersection of those boxes. Again, there are two scenarios. If they have transverse intersection, we again can show that using some L2 Cordoba argument shows that the locally, if those boxes intersect transversely locally, it should fill out a larger ball. So we can again use some thickening argument. If the boxes has tangential intersection, that means that that means that if we put them into suitable envelope and rescaling, they become again tube intersection, and those tube intersection will recover to the previous problem. So we go back to the first step and iterate. So that's a very quick sort of proof idea by pictures. And here, let's just summarize the winning strategies. So this previously was proof by pictures, now we summarize those pictures. So the first one is, the first case is when multiplicity is small, when the grains is Kastel. And that's like we summarize the winner structure depending on the outcome of the factoring proposition. And if the grains are, if the boxes are thick, then we have, with the winning strategy is to show some large local density and thickening to thick tubes, and then use induction. And then finally, when the grains become wider, in particular, if the grains become when I say the grains become wider, means that if the boxes are very thin but very wide, and the extreme case when it becomes two slabs, and then we can use some reduce to a two-dimensional Cordoba argument and conclude. So I guess that's the end of my talk. Thank you very much for your attention.
Other questions?
At the beginning, you mentioned the enemy counterexample with like you would go into the details at the end. Could we see that?
Yeah, thank you. Yeah. Let me add another page. Yeah, so this is a fun exercise. So the question is the following. If we have a rectangular box that contains at least one delta tube, how many distinct delta tubes at most can we put in U? So that's the question. Is the question clear?
Yes.
Okay, so now let's try to see it. So I claim that the number of tubes is at most the volume of U divided by the volume of T squared. Why there is this square? So let me try to make this picture larger. And if we want to, we can think about some extremal cases, like what happens if U is the entire unit ball, and what happens if U is a slab. So let's say in R3. So in R3, so when U is a tube, when let's say A is larger than delta. So what is the maximum number of distinct delta tubes containing an A tube? It is A divided by delta to the fourth. Why? Because we have A over delta square many distinct directions. And in each direction, we can pack A over delta square many parallel tubes. So that gives us A over delta to the fourth, which is TA over T squared. So is this part okay?
Yes.
Okay, now we have figured out how many delta tubes can we put in an A tube. Now let's consider the following. How many A tube can we put in an A times B times 1 plank? Well, this becomes a two-dimensional problem. So the maximum number of distinct A tube in an A times B times 1 plank is B over A squared. Using the same argument, we reduce the dimension, right? Which is also the volume of a plank divided by the volume of a tube square. So putting things together, so suppose U is an A times B times 1 box, then the maximum number of distinct delta tubes in this box is roughly A over delta to the fourth times to the fourth power times B over A squared, which is A times B over delta squared and then squared. This is the volume of the box divided by the volume of tube squared. Okay, I think that's the proof, and then you can probably generalize to higher dimensions.
Thank you.
Any other questions? So you mentioned in the beginning the enemy example in R3, and if you go to R4, the example becomes more complicated, or you have more than one enemy kind of secret?
Yeah, there will be more than one enemy example. Of course, the same enemy example still holds in higher dimensions. And I think maybe I actually learned this example from Josh. So in R4, this quadratic, if we take, let's say, let's call this quadratic Q, and we can take T to be maximum number of distinct. Okay, maybe I shouldn't say maximum number of distinct. So we can say T to be, this needs some calculation, but T, I think delta to the minus many delta tubes contained in the delta neighborhood of the quadratic. We can put this many in some smart way, and then this T satisfies like say Kastel-Wolff axiom, but but the volume of the union is equal to the volume of Q, delta neighborhood of Q is much less than number of tubes times T, also much less than 1. So this is a bad example in R4. So which means that for our Kastel convex Wolff axiom and Frostman convex Wolff axiom, we should in even higher dimensions, we should consider those neighborhoods of algebraic variety and also rules them out. So sorry, this becomes slightly more technical if we want to say what these tubes are. So basically we want to put this many, but inside this delta neighborhood of the quadratic as sparse as possible, but still this volume is like this becomes delta to 1/2, but the left hand side is delta. Yeah.
Thank you. Any other questions? If not, let's thank the speaker again.